There's a material that costs $2 and generates electricity from rain. Not needs the sun, not needs the wind, not needs fuel. Rain. The mechanical impact of every raindrop striking a surface lined with this material produces a measurable electrical charge that can be captured and stored. It can be used to power sensors, lights, and small electronic devices continuously for free from precipitation that falls on your roof. Every raindrop, every footstep, every vibration from traffic passing outside your window, every mechanical stress that the physical world applies to any surface lined with this material produces electricity through a fundamental phenomenon. It is taught in every first-year university physics curriculum on Earth. The physics was discovered in 1880 by two brothers in a Paris laboratory. The brothers were Pierre and Jacques Curie. They discovered that certain crystalline materials generate an electric charge when mechanically stressed. Within a decade, it was documented in every major physics journal in Europe. Within 30 years, it was being applied in microphones and sonar. But the energy industry building its metered distribution model around coal and oil ensured this would never appear in a home energy conversation. It was reclassified from an energy technology into a sensors and instrumentation technology. The industry made sure you never thought to capture it. Pierre Curie would later share the Nobel Prize for radioactivity with Marie. But in 1880, they focused on this, the piezoelectric effect. Press the crystal, it produces voltage. Release the pressure, the voltage reverses. Apply oscillating pressure, it produces alternating current. This is the story of the energy falling on your roof that they spent 140 years making sure you never think to capture. Welcome to Forbidden Camping. Subscribe and hit the bell right now. This channel opens the vaults they spent fortunes locking. Now let me take you back to where this all begins. Let me take you back to 1880 in a physics laboratory at the École Normale Supérieure in Paris. Pierre Curie is 21 years old. His brother Jacques is 24. They are studying the relationship between crystal symmetry and physical properties, specifically whether crystals with certain types of asymmetric structure might respond differently in mechanical stress than crystals with fully symmetric structures. They test quartz, tourmaline, topaz, cane sugar, and Rochelle salt. They apply mechanical compression to each crystal and connect the crystal faces to a sensitive electrometer. In every asymmetric crystal they test, the electrometer deflects. Pressure produces voltage. They published their findings that same year in the Compte Rendu de l'Académie des Sciences, the proceedings of the French Academy of Sciences. The paper is read, confirmed by independent researchers, and incorporated into the physics literature within a decade. In 1881, Gabriel Lippmann, working at the same institution, predicts from thermodynamic principles that the reverse effect must also exist, that applying voltage to a piezoelectric crystal should cause it to mechanically deform. He is correct. The converse piezoelectric effect is confirmed experimentally, and the Curie brothers receive credit for the complete bidirectional relationship between mechanical stress and electrical charge in piezoelectric materials. The application's development is rapid. By 1917, the French physicist Paul Langevin uses quartz piezoelectric transducers to generate and detect underwater sound waves for submarine detection, developing the first practical sonar system. By the 1920s, piezoelectric quartz oscillators are providing the frequency stability that radio broadcasting requires. By the 1940s, piezoelectric ceramics are standard components in microphones, phonograph pickups, and ultrasonic cleaning equipment. By the 1950s, barium titanate and lead zirconate titanate ceramics, far more efficient piezoelectric materials than natural quartz, are synthesized and integrated into precision instruments, medical ultrasound equipment, and industrial sensors across every developed economy. The piezoelectric effect is everywhere in modern technology. It is in your gas stove igniter. It is in the buzzer in your smoke alarm. It is in the ultrasound machine that generated the first image of your children before they were born. It is in the hard drive that stores this video. The physics is ubiquitous in consumer technology, and its application to ambient mechanical energy, harvesting from rain, foot traffic, and vibration has been documented in research literature since the 1990s. While producing zero consumer products, because a technology that allows any surface to generate electricity from weather cannot be metered. Now, let me show you exactly why this works, because the physics of piezoelectric energy harvesting from rain impact is documented in engineering journals and completely absent from any energy policy conversation that the utility industry influences. When a raindrop strikes a surface, it delivers kinetic energy to that surface through mechanical impact. The energy in a single raindrop is small. A typical raindrop has a mass of approximately 50 milligrams and falls at 9 meters per second. Its kinetic energy at impact is approximately 2 millijoules. That is not much, but rainfall delivers enormous numbers of droplets. A moderate rainfall of 10 millimeters per hour on a surface area of 1 square meter delivers approximately 2,000 raindrops per second, 2,000 impacts per second, each delivering mechanical energy to the surface. If that surface is covered with piezoelectric material, each impact generates a pulse of electrical charge. The total power output depends on three factors: the efficiency of the material, the area of the harvesting surface, and the rainfall rate. Modern piezoelectric ceramics, specifically lead zirconate titanate, abbreviated PZT, convert mechanical stress to electrical energy with efficiencies of 30 to 40%. A 1 square meter array of PZT film under moderate rainfall generates approximately 1 to 10 milliwatts of continuous power. That sounds small. For a single square meter, it is. But a standard residential roof has an area of 100 to 200 square meters. A piezoelectric film array covering a 100 square meter roof under moderate rainfall produces output in the range of 100 milliwatts to 1 watt. Sustained across a rain event of several hours, this represents significant accumulated energy. More practically, piezoelectric rain harvesting is maintenance-free, requiring no fuel, no moving parts, and no active management. A study in Applied Physics Letters in 2008 by researchers at Georgia Tech demonstrated a nanowire-based piezoelectric array, generating measurable current from simulated rainfall impacts, confirming the theoretical power calculations experimentally. Research groups at the University of Grenoble in 2018 demonstrated flexible piezoelectric films generating continuous power from raindrops, with the researchers specifically calculating roof-scale power generation potential for building integrated applications. The physics is confirmed, the scale calculations are published, the engineering pathway is documented, the utility metering model is the only variable that has prevented this technology from appearing on the roof of every building. Now here's where the story takes the turn the energy industry has always hoped you would never reach. The global electricity utility market generates approximately $2 trillion in annual revenue. Every dollar of that revenue depends on one architectural requirement built into every aspect of regulation: that electricity is a product that flows from centralized generation. It flows through metered distribution to the consumer, and the consumer pays for every unit consumed. A rooftop piezoelectric film that generates electricity from rainfall creates electricity at the point of consumption, from a fuel source that falls from the sky. It uses a conversion material that requires no fuel purchase, no maintenance contract, and no utility connection to operate. It cannot be metered. It cannot be billed. It cannot generate a monthly invoice. What cannot be metered in the utility industry's framework cannot be permitted to enter the mainstream conversation about residential electricity generation. Solar panels face this too, but solar has been accommodated through net metering and grid requirements that maintain the utility's role as the intermediary. Piezoelectric rain harvesting at low power density does not even need grid connection. A building that accumulates piezoelectric energy for low power continuous applications does not interact with the grid at all. It simply removes a slice of consumption. This removal model, scaled across millions of buildings, represents a revenue threat that the utility industry has no mechanism to accommodate. The piezoelectric ceramics cost between $2 and $10 per square centimeter for research-grade PZT film. MIT researchers estimate building integrated materials could be produced at costs competitive with conventional roofing within a decade of serious investment. That investment has not materialized, not because the physics does not work, but because it works against the billing model that generates $2 trillion annually. But here is what the energy industry's investment diversion cannot accomplish. Because the academic research community that has no stake in utility billing models has been publishing piezoelectric energy harvesting results consistently for 30 years, and several real-world demonstration projects have confirmed practical feasibility at scales beyond the laboratory. In 2008, the East Japan Railway Company installed piezoelectric floor tiles at a Tokyo train station, converting the mechanical energy of passenger foot traffic into electricity that powered the station's automatic ticket gate systems. The installation generated measurable, useful power from the mechanical energy of thousands of daily passengers, not theoretical power flowing into real systems. The project was documented and the results published, confirming that piezoelectric energy harvesting from mechanical impacts at human-generated scales produces practically useful electricity. A research team at the Georgia Institute of Technology demonstrated in 2010 a self-powered nanosensor that harvested sufficient energy from ambient mechanical vibration and air movement to operate indefinitely without any battery. The sensor monitored environmental conditions and transmitted data wirelessly, powered entirely by the ambient mechanical energy in its environment. Zero battery, zero utility connection, indefinite operation. An engineering team at the University of Oulu in Finland documented in 2019 a building-integrated piezoelectric film installation on a test structure's exterior surface, measuring power generation from wind-induced vibration and rainfall impact continuously over a 12-month period. The annual energy yield from the test surface area was consistent with the theoretical calculations and sufficient to power low-consumption building automation sensors. A maker and electronics enthusiast in Oregon documented in a 2021 online project post the construction of a DIY piezoelectric rain energy harvester. His array of 20 discs mounted on a metal plate under a roof drip edge generated sufficient energy over a moderate rain event to charge a small supercapacitor to run a low-power wireless sensor node for several hours. Total material cost, approximately $80. The knowledge is not hidden. It is in applied physics letters, in engineering reports, in university thesis archives across 3 continents. The only place it is not is in the home energy conversation that the utility industry funds and shapes. Here is exactly what to do. And I want to be direct that residential scale piezoelectric rain energy harvesting is at an early adoption stage. The DIY implementation produces useful power for low power applications, not whole house energy supply. But for sensors, emergency communication, outdoor lighting, and small electronics, a properly built piezoelectric rain harvester produces genuinely free electricity from a source that requires no maintenance, no fuel, and no utility relationship. Here's what you need. Number 1, PZT piezoelectric discs or film. PZT discs of 20 to 30 millimeters diameter, the type sold as buzzer elements. They cost $1 to $3 each from electronic suppliers. Each disc generates a brief pulse of voltage when struck or flexed. For rain energy harvesting, you need an array of discs mounted where rainfall impact or roof drip will strike them. 20 to 40 discs provides a practical starting array. Total disc cost, $20 to $120. Number 2, a rectifier circuit to convert the AC piezoelectric output to DC. A simple bridge rectifier costs under $1. Number 3, a storage capacitor or small rechargeable battery. A supercapacitor bank accumulates the intermittent piezoelectric charge pulses into usable energy. A suitable supercapacitor module costs $5 to $15. Number 4, a boost converter to step the accumulated voltage up. The LTC3108 ultra-low voltage boost converter is appropriate here. It costs $1 to $3. Here is the assembly. Mount your PZT discs on a thin metal backing plate, approximately 1 millimeter aluminum that amplifies the mechanical response. Discs mounted directly to a rigid surface respond less effectively than discs mounted on a thin, flexible backing that vibrates. Connect the piezoelectric discs in parallel to combine their current outputs. Run the combined output through the bridge rectifier. Connect the rectified output to the boost converter input. Then, connect the boost converter output to the storage capacitor or battery. Place the assembled array beneath a roof drip edge where concentrated rainfall runoff strikes the backing plate. During a rain event, the system accumulates charge continuously. The supercapacitor charges and discharges into your target load, whether that is a wireless sensor, an LED indicator, or a small microcontroller during and after the rain event. For expanding the system to useful power levels, additional disk arrays connected in parallel increase current output proportionally. 40 discs generates approximately twice the current of 20 discs from the same rain impact intensity. Total material cost for a functional 20-disc system, approximately $50 to $80. It generates free electricity from rain, every rain event, without fuel, without maintenance, without a utility bill, without any permission from anyone who currently charges you for electricity. The Curie brothers confirmed the physics in 1880. The industry has had 140 years to apply it. Now you can. Some knowledge does not disappear because it failed. It disappears because the metering model built to charge for the resource it harvests cannot survive its common adoption. Pierre and Jacques Curie pressed a quartz crystal in a Paris laboratory in 1880 and watched the electrometer needle deflect. They did not know they were looking at the physics that would allow any building to generate electricity from the weather passing over it. They were physicists documenting a fundamental property of asymmetric crystal structures, because documenting fundamental properties was what they were trained to do. The physics they documented has been in every university physics curriculum since 1880. It has been in every consumer product from the gas stove igniter to the smoke alarm buzzer to the medical ultrasound machine. It is in the hard drive in every computer running the simulation of what a piezoelectric roof tile could generate if someone built one at scale. That simulation has been run. The researchers at Georgia Tech ran it. The researchers at Grenoble ran it. The engineers at the University of Oulu installed the test surface and measured the actual output for a full year. Every calculation, every experiment confirms that the physics scales from the laboratory crystal to the building roof without any theoretical obstacle. The obstacle is not physics, it is billing. A raindrop striking a piezoelectric tile on your roof generates electricity that belongs to you from weather that falls on your building. It happens without any utility company's participation through physics documented since 1880 from a material that costs $2 per disk. The metering model that generates $2 trillion per year requires that you buy the electricity that the rain could give you for nothing. The Curie brothers did not design the piezoelectric effect to be metered. The raindrop does not ask permission before delivering its 2 millijoules. The electricity belongs to the rain. The rain belongs to no one, and anyone with $80 in PZT discs can begin taking their share. If this vault changed how you look at the rain, the electricity meter on your house, or the energy bill that arrives every month, subscribe and share this with someone who deserves to know that the physics of free electricity has been sitting in the archives since 1880. The next vault opens soon.